We are discussing electric circuits course of second semester students. This course is offered in spring 2020, the textbook, and I am Dr. Khalid Hassan in the Department of Electrical Engineering. Today's lecture is on chapter 6, and chapter 6 discusses first and second order circuits. Note that only first order circuits are included in this course, and first order circuits are discussed in section 7.1, 7.2, 7.3, and 7.4. This is part 1 of lectures on chapter number 6. Next lecture will be part 2, where we will discuss first order circuit response to exponential and sinusoidal inputs. RC and RL circuits are first order circuits, and in the following discussion I will explain how we can determine the order of the circuit. You know that capacitor is an energy storing element and inductor is an energy storing element. And due to the number of energy storing elements in a circuit, we determine the order of the circuit. If we have only one energy storing element, whether it is capacitor or inductor, it is first order circuit. If we have two energy storing elements, means two capacitors or two inductors or one capacitor and one inductor, then it is second order circuit, and so on and so forth. Note that if two capacitors are connected in series, it will be considered as one capacitor, or if two capacitors are connected in parallel, it will be considered as one capacitor. So we will use the equivalent capacitance, whether in series or in parallel. Similarly, the inductors as well. So how we analyze the dynamic circuits? Dynamic circuit means their voltage and current, they change with respect to time. So we begin by selecting a linear circuit, and given the linear circuit, we then write differential equations. We use node analysis, we use loop analysis in order to find differential equations. Then we solve these differential equations. There are many methods to solve the differential equations. We will discuss only one method. And various methods in the solution of differential equations are part of mathematics course on differential equations. And I think you have studied it in semester 1, or perhaps you are studying in this semester as well. So if we solve the differential equations, then we have the response of the circuit, and we then plot the waveform. Response means we may be analyzing the circuit in order to find the voltage across a circuit element or current through a circuit element. This is known as response, either voltage or current. And we sketch the waveform in order to see the dynamics of the response, and that's it. In writing differential equations of RC and RL circuits, in the beginning I will discuss circuits consisting only one capacitor or one inductor. We may have more than one inductor than more than one capacitors. You will see many circuits in the following discussion. So how to write differential equation? The shaded part of the circuit, it may be a bigger circuit, but the whole of the circuit is represented as its equivalent circuit with the help of Thevenin resistance and Thevenin voltage. And you know the meaning of Thevenin resistance and Thevenin voltage. Basically, we may have many other components over here, but no capacitor. All energy storing elements are shown at the right hand side. In the present case, we have only one capacitor. So in this is a voltage source and the resistance, equivalent resistance or Thevenin resistance. We have inductor here, and the whole of the circuit which excites this inductor is represented with the help of Norton equivalent. We have deliberately used Norton equivalent with the inductor and Thevenin equivalent with the capacitor. Later, we'll discuss that we prefer capacitor voltage. We prefer capacitor voltage in our analysis instead of capacitor current. And we prefer inductor current instead of inductor voltage. And then we will call the capacitor voltage as a state variable and inductor current as a state variable. How to write the differential equation of this? It is basically a loop equation. If we move around the loop in the direction indicated by the cursor, so the voltage drop over here in the direction of the current, this is RT, IT, and this is the voltage drop VT, which is the capacitor voltage, and this is voltage rise. So this is loop equation. It is a loop and mesh as well because we have single loop. Now, as we know that capacitor current is the product of capacitance and time rate of change of the voltage, we will use this expression of I and we will substitute I in the first equation. So if we use this I equal to C dV by dt in this equation, where it is RT, I is C dV by dt plus V over here, and this is the right hand. This is first order differential equation. This is a variable which will be called as response of the circuit. This is the capacitor voltage in its natural form, and this is first order derivative. This is first order differential equation, and this is the right hand side. In the right hand side, this VT is the excitation to the circuit. Excitation or the external input to the circuit is shown at the right hand side. All capacitor voltage terms, whether in normal form or in derivative forms, presently we have first order derivative, we may have second order and higher order derivative. So all V terms, VT terms are capacitor voltage terms are expressed in the left hand side, and all the remaining terms at the right hand side. Now look at this. Here we use node equation. So towards this node, this current is flowing towards the node shown at the right hand side. Current leaving the node in the direction of the cursor in the downward direction, this current. So what is this current? This current is the voltage across this divided by the resistance. So the voltage is the inductor voltage, and this current is also leaving, so this is I. So this is our node equation written over here. We know that voltage across inductor is the product of inductor and time rate of change of the inductor current. So we substitute VT in here. So in this equation, this is substituting this, we have L di by dt. This is V divided by Rn. This is the current flowing through the resistor, and this is the current flowing through the inductor, and this is the current flowing towards the node. So it completes the equation, and this is a first order differential equation. A variable capacitor voltage is known as state variable, and inductor current is known as state variable related to inductor. Recall that IL appears in the energy storing expression of the inductor, which is 1 by 2 multiplied by L I square, and the energy stored in the capacitor is equal to half CV square. So the voltage, capacitor voltage appears in the energy stored expression of capacitor, and inductor current appears in the energy stored expression of the inductor. So inductor current, if we know the inductor current and the capacitor voltage, we can determine the remaining voltages and currents in the circuit. Now again, RC circuit, and we have seen this first order differential equation response of the circuit, which is the voltage. This voltage is the response of the circuit. This voltage, which is the capacitor voltage, it depends on number one, inputs driving the circuit. So we have one input, we may have more than one inputs. So the voltage depends on the inputs or external excitations in the circuit. Number two, values of the circuit parameters, resistance and capacitance, RT and C. And then the value of voltage at T equal to 0. If we start analysis, our analysis of this circuit at T equal to 0, then there may be some energy stored in the capacitor, and due to this energy stored in this capacitor, we'll have some voltage across the capacitor, and this voltage will be known as initial voltage, and generally this is the initial condition related to this circuit. For zero input response, we remove all the external excitation expressed to the right hand side, we equate it to 0. You may wonder that if there is no external excitation, then how some current may be flowing in the circuit and how some voltage may be appearing across circuit elements if the external excitation is 0. External excitation 0 and still there is some voltage or current means that the circuit dynamics is due to the stored energy in the circuit, and the stored energy will determine the initial condition. However, this equation with right hand side is equal to 0 is known as homogeneous differential equation. Eliminating the voltage excitation, making it 0 means we short circuit. You also know that if we eliminate a current source, we leave it open in order to make current 0. So in order to set the voltage to 0, we remove the voltage source and then we short circuit this to ensure that voltage across these two points is 0. Now how current may be flowing in it? There is no voltage source. So if there is some voltage across the capacitor due to initial condition, then this voltage may be a reason of the current flowing in this loop in either direction. It depends on the polarity of the initial voltage across the capacitor. Right hand side, I have said this, right hand side 0 means the external excitation or input is 0. Differential equation with 0 excitation means right hand side is 0 is known as homogeneous differential equation. Now 0 input response of the first order RC circuit, 0 input, we have made the right hand side equal to 0 shown over here, and right hand side 0. This is homogeneous equation. Now how to solve this differential equation? There are more than one methods in the solution of differential equation. We will use the simple one. As we know, there are two terms, and sum of two terms is equal to the right hand side, which is equal to 0. So we have voltage over here, and this is the derivative of the voltage. This situation demands that this voltage, this Vt, must be similar to its derivative, dV by dt. They must be similar, and the one function which qualifies this property is an exponential function, because if we differentiate this, it will be SKEST. So SKEST, SK will be the coefficient and EST will be the same as that over here. So this will be an exponential function or term, and this will also be exponential function or term, and the coefficient will be different, and the sum must be equal to 0. If our assumption of Vt equal to Kest ensures that the sum is 0, it means that this is the solution of the equation. Now, if we substitute Kest in here, so then it will be Rt d by dt of Kest. So it is d by dt of Kest is Ksest, and second term is Kest, as we have said before. Kest is common, and then we have RTCS plus 1, and from here we have S equal to minus 1 over RTC. Note that we have assumed a solution, and in this solution two things are unknown, K and S, exponential. We know the exponential function. So if we can determine K and S, then it will be enough to find the solution. So S can be found using the substitution. You have seen S is equal to minus 1 over RC or RTC. Now we substitute S in this, and KERT minus T divided by RTC. Now in here only K is left to be determined. How to determine this K? We use the knowledge of initial conditions, and the knowledge of initial conditions means if we can find the voltage at t equal to 0. This is the initial condition. So substituting t equal to 0 on both sides, so V naught means V0 means the initial voltage across the capacitor Ke, so it gives us K, and this V naught is the voltage at t equal to 0. So this is the initial voltage across the capacitor, as it is a constant value, some constant voltage across the capacitor right at the instant of t equal to 0. So K is equal to V naught, and then our solution is we have found K, we have found S, we have found K and S in it. So this is the solution for t equal to or greater than 0. In here, the time constant term is in the denominator of the power of exponential function. So T divided by RTC. So RTC is known as time constant, and we also use letter tau to represent TC, means time constant. So time constant of RC circuit is RC, R multiplied by C, and the unit of this time constant is seconds. And if we, due to some initial voltage, if there is a voltage, say with this polarity, some positive voltage with this polarity, and this is V naught, so we just substitute t equal to 0 in this equation. So t equal to 0, it will be V naught, and then we have discussed in our previous lectures on chapter 4 that this is the property of an exponentially decaying function, that it reduces to 36.8% of its previous value after each time constant. So if t is equal to 1 RC, so this is t equal to 1 RC, so it is this value is 36.8% of the previous value. If t is equal to 2 RC, means 2 time constant, then this value where I have placed this cursor, this will be 36.78% of this value. And moving further, if t is equal to 4 time constant, 4 TC over here, this value where I have placed the cursor, this is about 2% of the initial value, and we assume that it is almost 0, because after that the value will be so small that we can neglect. Now in this slide we will discuss how to analyze the RL circuit. So we have chosen the equivalent circuit a Norton equivalent circuit, purposely note that we may have a resistance and a voltage source, but we prefer this to generalize the result. This is not essential. We may have a resistance here and voltage over here, and you know that we can transform current source into voltage source and vice versa. Now in here, in the previous slide, you have seen that this is the differential equation, and when the excitation is zero, this excitation is zero, we remove the current source and leave the circuit open like this. This is the open, no current is flowing through towards or from this node like here. And then right hand side, because we have removed this IN, right hand side is equal to 0, and we do the same. We use the same method as in case of RC circuit in order to find the solution. IT is equal to I naught E minus R N T divided by L. Note that in case of RC circuit, the power was minus T over RC. So we can represent it like, listen carefully, we can represent the power as T divided by L over R, L over R. So L over R is the time constant of an RL circuit or LR circuit. This is the time constant. Zero input response in the first order circuit depends on two quantities. Again, the circuit time constant and the value of the state variable at t equal to 0. In its zero input response, this zero input response, it depends on the time constant L over R. It is slow or fast. If time constant is slow, the current will be decaying slowly. If it is fast, it will be decaying quickly. And the initial value, what is the initial value of the state variable? State variable related to inductor is the inductor current. Capacitor voltage and inductor current are state variables because the knowledge of these two state variables is enough to determine the amount of energy stored in the circuit at any time, and in order to determine the rest of the voltage and currents in the circuit. Now, time constants in RC circuits and LC circuits when we may have more than one resistors or inductors or capacitors. So, time constant of RC circuit is equivalent capacitance and equivalent resistance RC, and in case of RL or LR circuit, this is L over R. Now this is a circuit where we have one energy storing elements and more than one resistors. So in here L equivalent is only this inductance, and we will see the equivalent resistance seen by this inductance. Equivalent resistance seen by this inductance means resistance from here to here. So we have two parallel resistors over here and then series. So we see that R equivalent is parallel combination of these two. This should be parallel. So it is this should be a R1 R2 here. It is a parallel combination, and the parallel combination of R1 R2 is R1 multiplied by R2 divided by R1 plus R2, parallel combination. This was a typo, be careful about that and note it. Now this parallel combination is R1 R2 divided by R1 plus R2 plus R3. So this is R equivalent, and what is the time constant? It is L over R. Now in this case we have two inductors and two resistors. We find equivalent inductance and equivalent resistance. So equivalent resistance, now resistors are in series and inductors, these two inductors are in parallel. This end and this end of both inductors is connected together, and other end of L2 is connected to the other end of, so this is parallel combination of inductance. So we find equivalent inductance and equivalent resistance in order to find the time constant of the circuit. We have third circuit, we do the same. We find the equivalent capacitance. Now C1 and C2, remember when capacitors are connected in series, the equivalent is C1 multiplied by C2 divided by C1 plus C2. This is different from resistors. So it is resistors are connected in parallel, and this is R1, R2 is here is another typo. Be careful about this. This is shown in the subscript. This is shown in the subscript. This is over here. So actually, I wanted to write R1, R2 divided by R1 plus R2, and two capacitors are connected in series, and if connected in series, the equivalent capacitance will be C1, C2 divided by C1 plus C2, and then we find the equivalent capacitance, and due to this we determine, we calculate the time constant. So in this circuit we have one capacitor and more than one resistors. We will use this you can say it is a circuit element, or like this is a switch, and due to this arrow it means that normally the switch is open, and at t equal to 0 we close it, and t equal to 0 is the time instant when we start the analysis of our circuit, and at this time instant when we close the switch we determine the initial voltage across the capacitor or initial current flowing through an inductor due to stored energy in these energy storing element. So in here this capacitor, so resistance, equivalent resistance seen by this capacitance is 10K plus parallel combination of this, 10K plus parallel combination of these two. So this is 20K, 20K, parallel is 10K, 10K plus 10K is 20, and capacitance is 0.5 microfarad. So the time constant is a product of R equivalent and C equivalent, which is 10 millisecond. I advise you to verify these calculations, because in preparing slides there may be some typo in it, so please verify these calculations. Now in this example we want to see the response of the state variable of RL circuit. State variable is inductor current. Same current is flowing through two inductors. So if we know the current, then subsequently we can find the voltage. It is L2 di by dt, L2 di by dt. Knowing these two voltages, we can find the voltage across these resistors. So knowing the voltage across these, we can find the current, through R1 and R2. So it means that basically we require the knowledge of inductor current, and inductor current is a state variable. Values are given, values of all components used in it are given, and initial value is also mentioned. This is the initial value which is mentioned over here. This is IL at t equal to 0 is 100 milliampere, and it is also represented as I naught. Now we find what is L equivalent. As in series, inductors in series, they are summed like resistors. So equivalent inductance we find, resistors are in parallel, we find the equivalent, and then we find the time constant, which is 26.6 microsecond. And this is the solution. IL, I have represented over here. IL over here means IL means this current which is flowing through both of these two inductors which are in series for t equal to 0. Now this is the initial value I naught, the initial value mentioned here 0.1, and E minus t over tau, and t over tau is shown over here. So we use this t over Tc. So then we can find IR1 as well. So if we know the current over here, we can find the current and we can find the current. So please verify this. All the calculations you need to verify. Now this is another circuit. We see the zero input response. Apparently, it may look a complicated circuit, but it is not. You know the dynamics of the circuit and you are able to write node equations. And we try to write node equation. First of all, we assume some directions of the currents. This is I1, this is IN, means going to the flowing towards the inverting input, and later we will say that IN is 0 as we are using the ideal operational amplifier model. So what is this current? What is this current? We will show it over here. So I1. So this is I1 in the direction shown. I1 is this voltage minus the voltage at this end, means Vs with respect to the ground. This is Vs minus Vn divided by R1. Vs minus Vn divided by R1. What is I2? This is I2. Due to the direction of the current, this is voltage at this end minus the voltage at this end. VO. This is VO minus Vn. VO minus Vn divided by R2. What is the current flowing through this? Capacitor current is C dV by dt. So it is C. What is the voltage across the capacitor due to the direction of the current? This is VO minus Vn. So it is shown over here, and this current is leaving. All these three currents are flowing towards the node. So they are assigned positive signs, and this current is leaving, shown as negative sign. We will leave this IN because we are using the ideal model of operational amplifier, rearranging these terms over here. So where Vn has gone, there is no Vn term over here. Vn is basically due to the model of the operational amplifier we are using. We are assuming that the voltage difference from here to here in either direction or polarity, the voltage is 0. We assume this voltage is 0. So this is at ground level. Voltage difference is 0. This is also at ground level, as it is not directly connected to the ground level, but the voltage is 0. Therefore, we call it virtually grounded point or node, and Vn is 0. So we take Vn 0, consider Vn 0, 0, 0 over here, and this is 0, and this is the resulting expression, the equation. And from here we can find we can rearrange these terms in the form of a first order differential equation. You know, this is VO and derivative of VO, and all non-VO terms are shown at the right hand side, and non-VO terms are Vs. So this is the excitation, external excitation to the circuit, or we also call it forcing function. And if we solve this differential equation for its natural response, we equate the right hand side is equal to 0. Natural response is the response of the circuit which is without excitations, and the response is due to stored energies. For example, if you are sitting in a room and the ceiling fan is turned on, blades are rotating, and you then turn off the ceiling fan, but it's still, after turning off, after switching off, the ceiling fan will be rotating for quite some time, for say half a minute. So why it will be rotating? It is due to the stored energy in it. Like if you have a kettle, and electric kettle maybe, and if the switch is on and there is some temperature of the water or milk or whatever, you remove the kettle from the burner or switch off the kettle, but the temperature of the water will not change suddenly. It will decrease exponentially. It is due to the stored energy in it. You are driving a motorbike and you suddenly turn off the engine, and still it will be moving. It will be due to stored energy. So stored energy is the reason of the circuit dynamics in zero input response. And right hand side means this is zero input response, and here while the coefficient of d by dt term is unity, if the coefficient of d by dt term is unity, then the coefficient reciprocal of the coefficient of VO term will be the time constant. And the output voltage is, output voltage, we have derived this expression before. This is the initial voltage multiplied by exponential function raised to the power minus t over tc. For t equal to 0 or greater than 0, and knowing tc and knowing the initial value, we can sketch the response. First order circuit response continued. Step response now. Step response means the right hand side is not zero. So UT is a mathematical necessity, or for more clarity we use UT, but usually you will not see this UT over here, and you will see only VA, or its numerical value may be given 12 volt, minus 100 volt, 5000 volts, whatever. So we will assume that we are starting our analysis at t equal to 0, and before t equal to 0 there is no voltage over here, and we are analyzing the circuit starting our analysis at t equal to 0, and at this time instant t equal to 0 we will find the initial conditions in the circuit in order to find the response or solution. And VA, we can omit this now with this assumption for t greater than or equal to 0. If we say that for t equal to or greater than 0, we can leave this, and this one may be omitted. Okay, this one may be omitted. This is an equation, and in this equation we will find how to solve this equation in order to see the response. Now, a circuit in the presence of external excitation, its response will be sum of two types of responses: natural response and forced response. Natural response is the response of the circuit when the right hand side is equal to 0, and we have seen it in the previous slides. And the forced response, this part of the response is due to the forcing function. This is the forcing function or excitation. As the circuit is linear, the response will be sum of these two. Total response will be the sum of these two. And in this, we will be finding capacitor voltage, because it is a state variable. First, we will find capacitor voltage, and then due to the capacitor voltage, we will find current, because current is C dV by dt. Knowing the current, then the current over here is also same, and we can find the voltage over here. So here voltage and current known, voltage and current known, this is the source, and it completes our analysis. Symbolically, we use the response VT, natural response, and forced response. For natural response, we equate right hand side is equal to 0, and we have derived this before. Now we will not find K by applying initial conditions at this stage. We will leave it here, and let us see how we proceed further. For forced response, the right hand side will not be equal to 0, and whatever is the voltage, we are considering DC voltage or constant voltage or step voltage or step response. So it's not AC voltage, it's DC voltage. We will discuss the circuit response to sinusoidal excitation. Now the forced response will depend on the type of the forcing function. Because our forcing function is a constant, our forced response will be constant as well. So we assume Vf is equal to a constant. You can consider it is the K1, and we substitute Vf equal to K1 in this. So if this is K1 and RC d by dt of K1, K1 is constant and this term will be 0 and K1 will be equal to Va. So our force response is Va. Now our completer, okay, this is, sorry, this is again, there is some typo over here. Completer, no completer, it's complete response. So the complete response is the natural response plus forced response. This is the natural response and this is the forced response. Only one thing is unknown in this response, which is K. And we will see how to determine this K. How to determine this K? We use initial conditions. What are initial conditions? We substitute t equal to 0 in this, and V at t equal to 0 can be represented as V naught. We usually represent it. This is just a symbol of V naught. You can use V parenthesis 0 parenthesis close, but this is a compact notation. Is equal to, look at this side, K, and this term over here, if we substitute t equal to 0, everything will be 1 and we will have K plus VA. And from here, we find K. What is K then? K is V naught minus VA. So this is the complete response for t equal to or greater than 0, and this is known as step response. In case of inductor RL circuit, this will be the step response. In the step response, this is the initial value and this is the final value or steady state value, and this is also final value or steady state value. We confirm it by applying limits. If the time approaches 0, 0 plus means 0 plus is a concept of time, means if this is time axis, and this is the origin 0, and if we approach this 0 from this side, we will be touching the positive side of this Z, and if we approach this 0 from this side, it will be 0 minus. So it's just one point, and we are just touching this 0 from positive side. It will be 0 plus. If we touch from this side, it will be 0 minus. This concept is usually used in science and engineering in the analysis of dynamic circuits. So we use limit of time approaching 0 in this. Limit of time approaching 0 means this term is 1, so V naught minus VA plus VA, so this is V naught. So this V naught is the response at t equal to 0. If t approaches infinity means this term will disappear, the whole will disappear, and this will be VA. And if you can recall, in the previous slide I said that V naught is the value of the voltage, capacitor voltage at t equal to 0, or this is the initial value and this is the final value or steady state value as t approaches infinity. The step response of the first order circuit depends on three quantities: the amplitude of the step function. This is the step response. It depends on amplitude of the step function VA. We are using VA. It depends on the circuit time constant. And this is RTC, RL, and RN. So there is some typo in it. I will correct this, make correction over here. It depends on the circuit time constant. I wanted to write basically over here. I wanted to write C, RT and multiplied by C, and I wanted to write L divided by R, L over R and RC. It also depends on the state variables, initial value of the state variable. So three things: initial value of the state variable V naught, this is the excitation, and the time constant. Zero input response and zero state response. This is the complete response. So what is the meaning of zero input response or zero state response? And transient response and steady state response. You know, this response is for t equal to or greater than 0. As we proceed with the time, as we move along the time axis, this exponential term will become 0, it will decay to 0, and it will eat up everything over here. It will eat up everything over here, and this will be the final value. So there will be some dynamics in the circuit initially, and finally this dynamic over here, all the changes will fade away, leaving the final value. So these changes are known as transient response, and as time t approaches infinity, only term which will be left is VA, and VA is steady state response. Steady state response is the response as t approaches infinity. Transient response is the response from when the circuit voltage or current is settling to some steady state value. Response of RL circuit, it is this is RC circuit and this is RL circuit. Now we rearrange these responses, means VO is shown separately and VA and VA terms are shown separately. So VA minus VA multiplied by exponential function VA minus V times the exponential function, and V naught. So we have separated two things. We have separated over here, we have separated this V naught initial value and the input or excitation. Response due to excitation is known as zero state response, and response due to zero the initial values is known as zero input response. So initially you may be a bit confused about the names we have used. What I'm saying over here, that the response, this response, when VA is equal to 0, means when input is equal to 0, external input is equal to 0, this will disappear and we will have only this. Because we have made input 0, therefore this response is known as zero input response. And this response, when all initial conditions or when all initial states are 0, means all VOs, this is the initial state, initial value or initial state. When we make this 0, we'll have this term only, and this term is known as zero state response. Similarly, the RL circuit, as RL and RC, the responses are dual to each other. Voltage is replaced by the current, voltage replaced by the current, voltage replaced by the current. Exponential function is same. The time constant here is RC, the time constant over here is L over R. We have a circuit RC or LC. So considering the response, we have the circuit response is due to two things. Due to initial value I naught, this is the initial value I naught or V naught, and due to input. And due to input, it is Vs or Is. I have shown these in a general form. This may be AC input and or AC voltage, AC current, or DC voltage, DC current. And due to these two, we have a circuit response. Initial and final conditions should not be difficult or new to you. This is the initial value and this is the final value. Initial value means as VC equal to VC at t equal to 0, and final value of this V means V when time t approaches infinity. Initial value minus final value and final value. This is just another representation. The state variable for t greater than or equal to 0 can be written in this form. The state variable means the capacitor voltage and inductor current. It can be written state voltage. This may be voltage in case of capacitor and current in case of inductor. This is initial value. This is not new to you. This is just shown in text. What is this initial value? What is this final value? Initial value, final value. Exponential function is same. And what is this? This is the final value. So this is we use the same expression in order to find initial value by substituting t equal to 0. This is the initial value, and we use the same response in order to find the final value as time t approaches infinity, and this is the final value. Now, initial and final conditions continued for the circuit shown below. The switch is shown over here. Note that what is the present position of the switch? Presently, the switch is closed. So these two points in the circuit are connected together. Circuit is closed, and following the arrow, the circuit is opened at t equal to 0. Note that if the circuit is closed for a long time, if circuit is closed, it will appear like this. The switch is closed. If the switch is closed, it will be like this. So when the switch is closed for a long time, what will be happening? Current will be flowing through this resistance R2 and through this capacitance as well. So due to the flow of the capacitor, current in the capacitor voltage will be increasing due to stored energy in it. So capacitor voltage will be increasing, and a time will come when this voltage will oppose any flow of the current, and it will make current equal to 0. So if the current becomes 0, though we have voltage over here, now the current will be flowing through this resistor R1 and R2. So initially current will be flowing through R1, splitting into two parts, R2 and through this. So this current will be charging the capacitor, and capacitor voltage will be rising, and the capacitor voltage will attain a value where it will stop any further flow of the current. And when no current is flowing through the capacitor, it will behave like an open circuit, OC open circuit. No current will be flowing. However, there will be some voltage across it, and this voltage is V0. This doesn't mean that this voltage is 0. V0 means if we then open the switch at t equal to 0, the voltage will be V0. This voltage value at t equal to 0 time instant when we will open the switch is known as initial voltage across the capacitor. Initial conditions. So go through this initial conditions. I have said it before. Capacitor current is 0, and the voltage across the capacitor is 0, and the current flowing, okay, this voltage, capacitor current will be 0, but the voltage will not be 0. What is the voltage? If you just ignore this, ignore this part, and only thing which is left, if no current is flowing, then the only thing is current will be flowing through this mesh only. So due to voltage divider principle, what is the voltage across this R2? It is R2 divided by R1 plus R2 multiplied by. So if we can determine the voltage, and this voltage is the initial voltage across the capacitor. Initial voltage means voltage at t equal to 0 is the initial voltage. Why it is not deleting? Anyway, the next, when the switch is opened, if we open the switch, note that some voltage has been initially stored over here. Due to stored energy, there is some capacitor voltage when we open the switch. Due to the voltage across the capacitor, current will be flowing in this direction, and the capacitor will be discharging Due to the flow of the current, capacitor will be discharging. So as there is nothing over here, this part is disconnected and no current will be flowing through this. Current will only be flowing through this R2 due to voltage across the capacitor, and capacitor voltage will decay to zero, will decrease to zero or decay to zero. And the final condition of the capacitor voltage when T approaches infinity is zero, because there is no excitation. Switch is open and there is no excitation. Equivalent resistance seen by the capacitor, equivalent resistance over here seen by the capacitance, it is just like a Thevenin resistance seen by the capacitor. For Thevenin resistance seen by the capacitor, we short circuit the voltage, and it is parallel combination of R1 and R2, and the time constant is RTC. Capacitor voltage for T equal to or greater than 0, we have derived this expression before, and due to initial conditions, it is the initial value of the voltage across the capacitor, final value, and this is the final value, and the final value of the capacitor is 0, capacitor voltage is 0, final value is 0, and V0 is equal to R2 divided by R1 plus R2 multiplied by VA. So this is the capacitor voltage for T equal to or greater than 0. And then knowing the capacitor voltage, this is the state variable related to capacitor. Knowing the capacitor voltage, we can find the capacitor current. So knowing the capacitor current, we can find the remaining currents and voltages. Initial and final condition continued. So the initial conditions over here, again I think it is the same thing, and the final condition, go through this, and the response is over here. It is the same example. So as there is some initial voltage which appears across the capacitor when the switch has been in this position for a long time, and it shows over here. This is shown here. This is T equal to 0. It has been, theoretically we say that switch has been in closed position from minus infinity to T equal to 0. The switch has been closed and there is some voltage which appears due to stored energy in the capacitor, and this voltage we have determined the voltage across the resistor, and this resistor voltage is R2 divided by R1 plus R2 VA, and this is the initial value of the voltage across the capacitor. Initial value of, as we know, the final value of the voltage across the capacitor is also 0, and this is the expression of the voltage. If we plot this expression, it will be exponentially decaying function or curve or waveform. Now the capacitor current is C dV by dt. So if we take derivative of this term due to negative sign, it will be a negative quantity. Look at this over here. This is the negative quantity, and this I will be starting from here. Note that why the direction of the current. So when the capacitor is charging due to the voltage, when the switch was closed, the current will be flowing in this direction. And when the capacitor is discharging, when we open the circuit, the capacitor is discharging, and this is the direction of the current when the capacitor is discharging. As we have written the differential equation, due to this direction of the current, then the opposite direction of the current will be negative, or negative current means the actual direction of the current is opposite to our assumed direction, for which we have written the differential equation and we have found the response. So it starts from this value and decays to 0. So very important lesson to learn in capacitor is that initially the capacitor current was 0, as we have said. Capacitor current was 0, it is fully charged, but there was some voltage, and then the capacitor current is like this. So current changes suddenly over here. So sudden change of the current is possible in capacitor, but sudden change of the voltage is not possible in the capacitor. You know, at just before T equal to 0, the voltage, and just after T equal to 0, the voltage is same. So it starts decreasing from its previous value. So this is the initial value of the capacitor, and just at the instant when we closed the switch, the current changes discontinuously. So this is possible. The abrupt change of current is possible in capacitor, as the inductor is dual of this capacitor. In inductors, sudden change of or abrupt change of current is not possible. However, voltage may be changing abruptly or suddenly in inductors. Initial and final conditions and circuit response. So this is a circuit I have chosen for you, and in this circuit, look at this, the switch. The switch is in position A for long time, theoretically from minus infinity to t equal to 0, and at t equal to 0 we move the switch from position A to position B. So as long as switch is in position A, this is the condition of the circuit. Switch is in position A, this is disconnected as if nothing is over here. So I have shown this voltage source over here. So due to this, what will be the state of the circuit? Ultimately, we want to find out output voltage, but first we find the state variable, and the state variable of inductor is IL. So first we will find what is the state variable, what is the response, and we see further when the switch is in position A for t less than 0, we find the time constant, and the time constant is L divided by R, or L equivalent divided by R equivalent, and we have only one inductance. Then R equivalent will be the inductance Thevenin resistance seen by this inductance. So Thevenin resistance seen by this inductance is this 50 ohm resistance, as we short circuit this, and 50 plus 25, and this is another parallel combination across it. So it is 50 and a parallel 50 on this side and 50 plus 25 on this side. So 75 ohm resistance and a parallel 50 ohm resistance. So from here we calculate R equivalent, and then we find initial and final values of the inductor current. So in this case, the response IL is over here. I'll explain it later, but look at this. When the switch is at position B, this is the condition. This is the when at B, this minus 10 plus 10, this source, it is connected to the circuit, and in B this will be disconnected. We will not show it here. Now again we will look at the state variable, and later we will find VO, and switch is in position B. We again see what is the time constant in it, initial and final values of the inductor, and we exploit this response by using initial values and final values and the time constant, initial value and final value and the time constant, and then we find IL when the switch is in position A. Okay, final value when the switch has been in position A for long time, and then we move the switch from position A to B at t equal to 0. Then we will see what is the final value of the inductor current, final value of the inductor current flowing through this. So as you remember, inductor, when inductor is saturated, when the current is settled to steady state value, it behaves like a short circuit. Capacitor behaves like an open circuit. If short circuited, the current flowing through will be 10 divided by 50 ohm. 10 divided by 50 ampere current will be flowing through this inductor, and no current will be flowing through this, because from here to here we have inductor and it is short circuited. The voltage from here to here is 0 and no current will be flowing. And this will be the final value of the inductor current when the switch is in position A. And at t equal to 0, we move the switch from position A to position B. So the final value of the current over here will be used as initial value of the current over here. Final value of the current, this IA will be used as initial value. So proceed further and you do it by yourself and find VO. What is VO? If we know this current, we can find then L di by dt, which is the voltage over here. And the polarity of this voltage will be L di by dt will be with this polarity. If the current is flowing in this direction, L di by dt. So if we know the voltage from here, from this node to this node, from this node to this node, which is the same, then L di by dt divided by 50 plus 25 will be the current which is flowing through this. So if we know the current which is flowing through this 25 ohm resistance, then we can find the voltage. So I advise you to do it by yourself, find it by yourself. This is end of part 1 of lecture on first and second order circuits. Again, remember only first order circuits are included in this course. It means the first order circuits are discussed in section 7.1 to 7.4, and the following lecture will be part 2 of first and second order circuit is chapter 7. Thank you.